Thank you very much, and welcome to my talk. Who here was on my talk yesterday? Thank you for coming back, and the rest of you, I will remember faces. So. Is this talk relevant? Who here doesn't use the internet? Oh, okay, so it should be relevant, right? All right, let's go. So just a recap, a little bit about myself. I do Linux at Cloudflare. I like operating system, infrastructure, security, and performance, and I enjoy low-level programming, Linux kernel drivers, bootloaders, and other scary stuff written in unsafe languages. But unlike yesterday's talk, I'm not going to deep dive. We'll have some low-level details, of course, but not very low-level talk. It's more about the internet, the architecture of the internet, and how to protect yourself. Cool. So let's actually try to get into context. Let's talk about distributed attacks on the internet. So, but before going to distributed part, let's just talk about denial of service attack, a simple one. So imagine you have a server. Like anyone here runs a web app or a server on the internet, or a resource. Yeah. So imagine you have your server, right, and a web application, and have your users. And basically, yeah, they try to access your service, but then comes an attacker, and they send some junk traffic to your server, and basically overloading it, and then basically your users cannot access your web resource, and they're unhappy. So what you typically do is, well, you kind of try to firewall the attacker, right? So you put some firewall in front, and sometimes it helps. So the load is reduced, and then the users are happy again. So simple in a simple case. But if we zoom out on the internet scale, so we might talk about distributed denial of service. So you're running like that for quite a while, but then more and more attackers come and send junk traffic to your web resource, and it gets overloaded, and your users are unhappy again. What do you do in this case? Well, you can probably hide your server from the internet, right? And put it some dedicated, what they call dedicated firewall, like a firewall box or a Linux box, which will be just running firewall, special Linux distributions around it. But more and more attackers will come, and then this firewall may be overloaded again. And in this case, there are companies which will help you and say hey, buy our specialized dedicated firewall, which will handle all of that, and it will be quite expensive. But the problem is it's bound to fail, because in a distributed case, more and more attacker traffic will send, attackers will come, you receive more and more junk traffic, and even this dedicated firewall becomes overloaded, and then your users will not be happy. What is the problem here? The problem here is that on internet scale, the adversary scales the attack horizontally. So what are these distributed attacks? They're usually botnets where people find vulnerabilities in internet devices across the world, and they basically are able to get compute resource very cheaply and spread out all over the world. But if you go the dedicated hardware security box approach, you're kind of scaling your defense vertically, and then you're limited at some point, right? Because the more powerful your box is, the cost grows horizontally. And one thing before lunch that you can take away from this talk, if you're rushing to lunch, that if you're building some kind of internet defense, to efficiently protect from global internet, distributed internet attacks, you need to think about global distributed internet defense. You basically need to scale your defense horizontally with the attacker. How do we do that, for example? Let's talk about internet addressing. Unicast. Anyone here knows what unicast is? Well, it's regular internet addressing. You have a server, it has an IP address, and users are able to, when they connect to your server, they type in the IP address, connect to your service, right? So there is also in modern world, when you build architectures, there's unicast with load balancing, but it's still unicast. So you have a load balancer, which has a public internet address, and you have a bunch of backend servers. So technically, users connect to your load balancer, and load balancer distributes the user request across the backend service. So you kind of can scale a little bit of horizontally here by scaling the backend service. In Cloudflare, we actually bet for this on a technology called Anycast. So Anycast is, we have a bunch of servers across the world, but they all share the same IP address. And the idea behind, and we're not using any special things here, we're just reusing how the internet was designed to work. So if you have users trying to access this web resource, depending on where the users are, the internet promises to deliver, to route the traffic to the closest location. And so naturally having like a single IP address all over the internet, like users access different servers across the world. The nice property about it, the same happens to an attack traffic. So if you have a global distributed attacker, their traffic is kind of spread all over across the world. So this is the current, like, not probably even current, it's quite old, Cloudflare Global Anycast Network. So like each of these dots is a Cloudflare data center somewhere in the world, and each of these data centers have many servers, and each of these servers have the same IP addresses all over the internet. So imagine like if you have an attack, it kind of distributes all over the place. So in this case, yes, both users' traffic and attack traffic are distributed all over the world, and we are not using any specialized security devices or hardware, just like how internet was supposed to work. And this gives us like incremental cost in adding more capacity to serve more traffic. So you just pop in a new data center, add service to existing data center, and it all naturally happens. And this gives us this horizontal scaling, which we can use to protect from global distributed attacks, but also as a side effect, we can also serve more users, because just adding capacity gives us the ability to serve more users. Now let's talk about internet hijacks. So who knows what is the internet? What is the internet? Internet is a network of networks. And these networks are called autonomous systems. So for example, and they're designated by a special number, and like this is a Cloudflare network, this is, I think, Google or Amazon. And these networks exchange traffic, right? So how does, like if I'm a user, right, I type 11111, how does the internet knows to which network send my traffic? These networks communicate between each other and to announce the IP addresses they own. And through the old protocol designed in the 70s called Border Gateway Protocol. Anyone heard about BGP? Network guys? Yeah? So yeah, these networks continuously announce all the IP addresses they own to the internet. And like the other network listen to those announcements, and it's like, okay, 1.1.1.1 belongs to Cloudflare, so like when there is a packet destined to that IP address, I will send it to the Cloudflare network. Good, right? But what is the inherent problem? Like the protocol was designed in the 70s, and it's kind of like based on a gentleman's agreement. So I announce what I own, but I don't announce what I don't own. And now we have a problem here that in modern internet, where a lot of malicious activity, like you can have a malicious actor start announcing IP addresses that they don't own. And this is how internet hijacks happen, and like the traffic is, instead of being sent to valid destination, is sent to the attacker's network. It's, in best case, it's just black hole. In worst case, you can be like phished or something like that. So how do you protect from that? There is a modern improvement on top of BGP protocol called RPKI. So basically, all the announcements, the basic idea behind that all the announcements on the internet should be signed. And but it kind of, it's like it's a two-party system. So like you should not only sign your announcement, but also you should expect other networks to verify these signatures before sending the traffic that belongs to you. And not, unfortunately, I mean, this is quite efficient in theory, because this allows us to kind of leave these announcements, distinguish valid announcement from malicious announcement, and kind of block attackers from hijackers from the internet. It's also very useful from reliability perspective because invalid announcements sometimes just happens from not because of a malicious attack, but some kind of like misconfigured network equipment. They happen all the time, and sometimes you see these global outages on the internet. The problem with this approach is that like the networks should not only sign their announcement, they should verify other networks' announcements. And currently, not all networks do that. And if you're interested, we developed this tool where you can go now and check if your current ISP is actually safe from the BGP perspective. Does it verify invalid announcements? So on the left, unfortunately, it's my home ISP, which doesn't. And yeah, like if you log in, if you browse the internet somewhere from the Cloudflare network, it works fine. So you can go and check. And if your ISP doesn't support it and your web resource into the ISP, you should definitely reach out to your ISP and ask them to implement RPKI. All right, CDNs. Who here uses CDN? Good, right? CDN protection is quite simple. So you have your web resource, right? And you hide it behind some kind of CDN. And then when users try to access your web resource, they go into their traffic as actually routed to the CDN. And the CDN will forward the traffic to your web resource minus some caching. And the also idea that this puts like CDNs in this nice position to provide security features, because when the attacker traffic comes in, the CDN should actually filter it and not send it to your web resource. Cool. But there is a problem with this design, is that in this case, your server still has a valid routable internet IP address. And if the attacker somehow learns your actual IP address, what they can do, they can send traffic to you directly by passing the CDN. And so technically, even if you're using CDN, they can overload your backend server, and like CDN doesn't help you. What to do in this case? So one of the solutions, like if in this case the attacker can reach your server over the internet, how can you protect them? Like, well, you don't run your server on the internet, just run it on localhost. Nothing can go in. But then how your users will access it. So some CDNs, including Cloudflare and many others, support this now. Another way of connecting to it, so it's called egress tunnel. So your server can be behind like several NAT firewalls. It can be like your home router or something like that, not internet routable at all, but it can establish outgoing connections to the CDN, so-called egress tunnel. So when both user and attack traffic comes into the CDN can use the established connections to forward the proper traffic back to your backend servers, where the attacker who wants to actually bypass the CDN, they have no idea how to connect to your backend server directly, because you don't have an internet routable IP address on your server. Cool? Clear? So yeah, the advice here, if you're using a CDN, do check if they have this feature and try to utilize it. Okay, so now we've been talking about distributed attacks on the internet, but you have noticed we kind of never blocked any traffic, apart from the CDN case, but we always trying to slice and dice the traffic. So like with any cast network, we don't block anything. If there is a lot of attack traffic, we just slice and dice it across all the data centers that we own. So if we zoom in into the data center level, what we see is, so this is the Anycast, so we're slicing and dicing the attack traffic. And if we zoom in into a particular data center, what we'll see is that the data center itself will still receive both good and bad traffic. Right? So what can we do on the data center level to improve our resilience to attacks? So if we can go technically with the standard typical unicast with load balancing approach. So you have a load balancer, and then it balances the backend traffic. You can kind of scale the backend capacity, but at some point, if you have too much incoming traffic for a particular data center, your load balancer can still be overloaded. And again, you may fall into the trap of buying a dedicated load balancer and growing your costs exponentially, but it's the same way it doesn't work in the internet scale. It may not work on the data center level scale because your data center could still receive too much attack traffic. So the cheaper idea to do that is to just reuse the equipment you already have. And most likely in any data center, you have a top-of-rack switch or a router. So you have this router, which all the servers are used to just connect the internet. And unlike in this case, the actual internet routable addresses are assigned to all the servers. So your router doesn't have an internet. Well, it does for management purposes, but like your web resource IP address is actually on your servers, and you can use a technology called ECMP in the data center to start announcing these addresses to a router. ECMP is a data center equivalent of BGP on the internet. So what it does is basically, if you start announcing to your router that, hey, I'm a server and I own 11111, the router will start sending you a portion of the traffic to the server. And this model actually gives you a very easy model to scale your data center horizontally to handle more capacity, because you don't need to reconfigure anything. If you need more capacity, you just add more servers. They have the same IP address. They just start announcing these new IP addresses to this router, and router automatically redistributes the traffic to all our servers. And the maintenance is easy as well. So if you need to put a server out of the maintenance, you just shut it down, it stops announcing, and the router stops sending the traffic to the server. So no special equipment here, just a router and servers and standard internet protocols. All right, so in this case, again, what we did here is no filtering of malicious traffic, right? Again, we're just scaling the data center to slice and dice if we have more traffic. So we just scale it across all our servers. So in this case, the traffic, every server can still receive the malicious traffic. So now let's zoom in into the server and see what happens inside. So now we actually, like, our server receives both good and bad traffic. So now we need to efficiently filter malicious traffic, right? Who knows what it does, what this does? Yeah, so yeah, this is a Linux firewall rule to drop all incoming connections. Do you think it's an effective way to deal with malicious traffic? Well, yeah, what I mean, like, yeah, you will block good traffic, but like you'll block bad traffic, yes? So like, is it still good or bad? Turns out, even if your intention is to block all traffic, that still is not effective. Because if your server receives too much incoming traffic, it can still be overloaded. And we actually have a blog post somewhere in Cloudflare history where we proved it. So we had a server, we put like a block everything firewall rule, and like with enough incoming traffic, it was still overloaded. Why does this happen? Because yes, your server receives good and bad traffic. So what happens in this case for bad traffic? So a packet arrives from the attacker, right? It arrives on the NIC, right? This is the low-level details I was referring to earlier. So what the NIC does when seeing the packet, it sends a hardware interrupt to the main CPU, and probably that interrupt is serviced by the driver in the operating system. So what the driver does, it allocates, in Linux, for example, it allocates a kernel internal structure called skb, which is designed to hold packet data. It copies all the packet from the NIC to this skb and re-enables interrupts, usually. Then what happens next? The driver notifies the data link layer, the layer 2 implementation in the operating system, I have a new packet, and passes the skb structure there. The data link layer parses the packet, so it parses layer 2 headers to the checksum. It can sometimes merge frames for better efficiency, whatever. It does some processing. Then it passes the packet to the network layer, layer 3, and what the layer 3 does, it parses the layer 3 headers. Modern network stacks can do GRO, GSO, connection tracking, L3 checksum, identify if this is a local packet or not, does it need to do a routing decision, and only then it reaches that firewall rule block everything. So only then it did all this processing just to say, oh, like, I have a firewall rule, let's drop this packet. So with enough incoming traffic, you still make the server to do a lot of work just to decide to drop the packet. And with enough incoming traffic, you can actually overload it in this way. So in Cloudflare, we utilized an open source technology, which is quite popular these days, called Express Data Path. It's based on eBPF. Who heard about eBPF? It's a hot topic in Kubernetes. Yeah, but basically, because it's based on eBPF, it's fast, it's programmable, and it's kind of safe. So you can write these BPF programs which run in the kernel context, and basically there is no risk they will crash your system if they're invalid. And the idea of XDP is basically that you can write your firewall rules in the eBPF programming language and basically run those rules inside the NIC driver, or if like modern network cards support this, you can run it inside the NIC itself. So what happens here is with XDP, basically, if you don't have hardware support, so your filtering will happen on the driver layer, and if you have hardware support, your filtering will happen on the NIC layer. So in this case, basically, we're dropping packets straight on the NIC, and the operating system may never see it. So even if there is a lot of incoming traffic, this BPF is very efficient. So it kind of filters out the attack traffic incoming to our server. But you kind of need to write these programs, right? In Cloudflare, we built a system called DDoS, or DOSD, basically. So every data center in Cloudflare sends a sample traffic to a centralized location, where that centralized location continuously analyzes the traffic for new attacks, and eventually generates these small eBPF rules and redistributes them to every server in the network, and then these rules or firewall rules get installed as eBPF programs on our NICs. We also have like these localized versions for faster feedback. So for example, if a new attack is coming, so we don't have to wait all this propagation to happen in the central location. And the nice property of it, if one of the data centers sees the attack, the local instance of the DOSD quickly learns about it and generates programs to block that attack efficiently on the NIC layer, but then it also feeds back the information to the centralized system, and if we see the same attack on every other data center, we can also block it as well already. Any Star Trek fans here? No? No Star Trek? Oh, I see one. It's like if you watch Star Trek, it's kind of Borg. I like to think of it as a Borg race, so they adapt to attacks. Okay, so this is how we filter the, and again, this is all based on open source technologies, so if you're developing it from scratch, you should look into this technology for your web resource as well. Like, and you don't even need to have hardware support to utilize it. So we talked about, in general, for network layer protection. Let's talk about a little bit about application layer protection. So I didn't have to go far. I just it's my spam folder in my email. So hey, I won one MacBook. I already have one, but I won another one. It's nice that Google actually tells me that this message might be malicious, but what if I click that link here, right? So it may contain malicious contents. The idea behind that, this is your computer, you're a user, and you may be running like several applications, and if you click the malicious content, in best case, your current browser session might be infected, and some credential exploitation may happen. If your system is outdated, most likely it can lead to further compromise, so other applications might be infected, and the whole machine will be infected as well. So what's the solution here? Hey, well, don't run any programs and you will not be infected, right? Well, technically, it's not feasible, though, of course. If you run programs, you can put it in some kind of sandbox. And like Google Chrome, for example, has a very extensive support for sandboxing their browser to protect from these attacks. But still, there are sandbox escapes because sandboxing is kind of always a race between an attacker and people who design these sandboxing. So they design more protection, but the attackers find more ways to escape these sandboxing. So a more efficient solution maybe just don't run your browser locally. So for example, some CDNs and cloud providers provide you with a feature called remote browser isolation. So instead of running your browser session locally for scary website, you can run your browser remotely, and it's kind of a very seamless experience. So you can browse anything you want, and you can click any links you want. And if you click a malicious link, that a particular session will be infected. But essentially, when you close that session, that it will be securely destroyed, and your local machine will never be infected. I think that's it. This is all I wanted to say today. So some conclusions here. I want to repeat that to protect yourself from global distributed internet attacks, you definitely need a global distributed defense. So vertical scaling will eventually fail. Don't fall for that trap. The network is a computer, and now in modern times, the internet is your security perimeter with like modern technologies, remote work, and applications running on public cloud. You cannot use a regular network-based security perimeter approaches like I will allow list particular IP addresses or something else. You kind of need to have every application needs to adhere to what the modern world of zero trust architecture, that it can connect from anywhere, and you have to have secure cryptographic credentials to actually allow it. And practice defense in depth. So as we just saw, you definitely need security on all layers of your stack, both in network and the application layer. So yeah, the more you have, the better chance you stand against global distributed attacks. Thank you very much, and I'm happy to answer some questions.